Hello and welcome to College Physics 1, Lecture 14, Newton's Laws, and Free Body Diagrams. In our last lecture, we introduced force and different types of forces. In this lecture, our goal is to go through Newton's 3 laws of motion and then introduce how we represent each of these forces we've discussed visually with free body diagrams. To begin, let's recap Newton's first law, because we did introduce this in our past lecture. In general, when we think of Newton's first law, we're considering any object that has no forces acting on it, none whatsoever. So, in theory, this is fairly unrealistic on Earth because almost everything has a force acting on it, especially because of weight. But that said, if we consider an object that has no forces acting on it whatsoever, then we can talk about Newton's first law. If the object is at rest, with no forces acting on it, it will remain at rest. I mean, this makes sense. I mean, you leave a pencil sitting on your tabletop, it's not going to move unless something acts to move it. And then, if the object is moving, with no forces acting on it, it will continue to move in that same direction, in other words, a straight line, and without changing its speed. It'll stay the same constant speed until something acts on it. Now again, this is somewhat hard to visualize on Earth because it's not realistic. So, that takes us to space. In many cases, the best example of this is an object moving through space. So on the top, I just put in an image from South Park of Kenny floating through space, but notice he's moving in a straight line and perhaps somewhat hard to tell, but at a constant speed. And then another great example is this dog that was in orbit around the Earth, so effectively experiencing 0 Gs. And as a result, in each of the frames of this animation, you can see the dog moving in a straight line and at a constant speed. Even when he's paddling in one of the frames, it's not changing his motion at all. So, this is Newton's first law. Again, this is just a recap. So this brings us then to something new. Here we're going to consider an experiment that we can't really do well or easily on Earth. In my class, in person, we can use an air track, that is a surface like an air hockey table where there's holes in it and air blown into the surface, so that anything laying on top of the surface can experience almost no friction, but even still, it's not a perfect experiment. So just consider a block on a frictionless surface. And then imagine you take a rubber band, put it around the block, and then you pull it. Specifically, you pull it to maintain a constant force. In other words, you aren't letting the rubber band compress or stretch at all. So it's staying at a constant force or a constant stretchiness. If we do this experiment successfully, we would find a number of different things. First of all, and this is the hardest one to visualize, the block pulled with a constant force, in other words, not letting your rubber band stretch or compress, would have to move with a constant acceleration. Meaning, you would have to constantly pick up speed. And again, even if we had the air track and I showed you it, it's hard to visualize it because you aren't the one actually moving the block. You'd have to feel how stretchy the rubber band is. But just try to visualize that. So, if you want to move something with a constant force, you would have to constantly accelerate it. The other two results of this experiment are fairly straightforward. The acceleration of the object would increase if you increase the force. In other words, if you pulled harder, the block would accelerate faster. And the acceleration would decrease if the mass of the block increased. So just imagine you try to apply the same force to an object that's 10 times heavier. Well, it's going to be harder to accelerate that object. So what we can do with this information is sort of combine it all into one big piece of information. The first statement we made was that with a constant force, you have a constant acceleration. And the acceleration will increase if the force does. So that's telling us that there is a direct relationship between force and acceleration. If force increases, so does acceleration. And then we say acceleration decreases if the mass increases. In other words, acceleration and mass are inversely proportional to one another. Putting all of that together, we arrive at Newton's second law. Newton's second law is a mathematical equation. It states an object of mass m, subjected to forces, be it 1, 2, 3, and so on, will undergo an acceleration given by F net over m, where F net is the net or total force, and m is the mass. So recognize on this left-hand equation that we see a direct relationship between A and F. We said that if you increase the net force, you increase the acceleration. But if you increase the mass, in other words, you increase m underneath this fraction, well then you're dividing by more, which means your acceleration would decrease. So this equation is what we just stated in our experiment. It's just a formulation to show it. Now this rearranges, of course, to one of the most famous equations in all of physics. F equals ma. I'd argue that this and probably E equals mc squared are like the two most well-known equations in physics. And for good reason. This is going to be an equation that we use throughout the next, 7 lectures probably. It's the premise of all the problems we're going to work out. And we'll actually see that an equation this small and innocent looking is not so much that case as we get into this further. Now, the only thing left to discuss on this equation is the units. Up until this point, we've introduced what force is, but we never said what the units of force are. This equation allows us to visualize that. We see F is equal to ma. M, or mass, is measured in physics in kilograms. A, or acceleration, is measured in meters per second squared. So, combine the two, you have a kilogram times a meter per second squared. That is the unit of force, a kilogram meter per second squared. But that's kind of ugly, and we don't like to work with that most of the time, so we just give it a new name. We call a kilogram meter per second squared a Newton, or 1N. This is what we use as the unit of force, the Newton. All right, this then brings us to Newton's third law of motion, out of 3. Newton's third law is an action-reaction discussion. So consider, for example, you are hammering a nail into a wall. Obviously, you with the hammer are applying a force to the nail so that it is punched into the wall. But the nail also pushes back at the hammer. In fact, you experience that as a recoil, right? If you hit something really hard with a hammer, you can feel that recoil in the handle. An even better example, perhaps, is if you fire a rifle or a shotgun with the stock of that weapon up against your shoulder. When you fire the bullet or the shell out the front, the weapon kicks back into your shoulder. You can experience that reaction. So in general, we don't have to be specific and say a hammer or a gun. We can just say, if object A exerts a force on some object B, then object B will exert a force back on A. This is a pair of forces that we call an action-reaction pair. Now I will note, I don't necessarily at a personal level like that term, action-reaction, mostly just because by definition, reaction means you see or experience something and then respond. These forces occur simultaneously, so it's not really that one happens and then the other one decides, hey, I need to apply a force too. They happen at the exact same time. But regardless, thinking of it as action and reaction is just a really easy way to remember what's happening, so it is useful. So Newton's third law says, in general, that every single force occurs as a member of this action-reaction pair of forces. And they have equal magnitude, so it's an equal force between the two, but they are pointed in opposite directions. So you commonly hear this is, for every action, there's an equal and opposite reaction. That's a common statement. So, with this, we now have a basic understanding of what forces are and the 3 laws of motion that govern them. These laws apply to any object, anywhere in the universe. And what's kind of crazy to think about is that this Newton's third law, this action-reaction, it's true for every single force. It's even true for the gravity of Earth holding the moon in orbit. The moon is also tugging on the Earth with an equal force. The difference is the moon is so much smaller that it orbits around the Earth instead of vice versa. But I digress. To conclude the notes part of this lecture, we have to introduce free body diagrams. Now, if you have my actual course, you will hear me say this a lot, but these are severely important. You really want to understand these. So, in the next slide here, I'm just going to step you through what a free body diagram is and how to draw them. And then for the remainder of this lecture, we're just going to work out problems, like questions together, so you can get some practice working with these free body diagrams before we try drawing them ourselves. So, in general, a free body diagram, or as I abbreviate them, FBD, these are diagrams that represent objects as a particle or dot, and then show all of the forces acting on the object as vectors, or arrows pointing away from the dot. So you'll see a lot more about what I mean here in just a few minutes, but let's run through the steps. The single most important step to all of this is identifying the forces that are acting on your object. If you don't know what forces are acting on your object, you can't draw one of these diagrams properly, and then you certainly couldn't work out the problem correctly. So really everything relies on you understanding the problem you have and then the forces involved within it. So, identify your forces. Steps 2 and 3 kind of go together, and they're hardly steps at all. For every free body diagram, you draw a coordinate system, in other words, an x and a y axis. And if you're along a ramp, like we discussed in the past, you tilt your axes along the incline, so that the x-axis is along the slope. So, really these all start by you just drawing basically a large plus sign on your paper, your coordinate axes. Don't forget to label them. And then, step 3, again, barely even a step, just draw a big dot at the center. So, at this point, all you've done is drawn a big plus sign and a little dot in the middle. Now, once you've identified your forces, you'll be able to draw them onto your free body diagram. So, draw vectors, in other words, arrows, representing each of the forces that you've identified. Last but not least, and I tend to forget this one myself or just not do it, I'd say that it's optional. I would still like you to do this, but you want to draw and label the net force vector afterward. You typically don't draw this directly onto the axes like you do with the other forces, though. A lot of times you'll just kind of draw this off to the side, just so that you, for your own sake, can remember what direction the net force will be pointing, if there is one. And I suppose I should add into step number 4, and it's very important, that you label each of your vectors. Otherwise, it's just a bunch of arrows on a page. So labeling them appropriately is very important as well, especially when it comes to me grading your diagrams, because like I mentioned, if there's no labels, I don't know what force you're thinking of, and it's just an arrow on the page. So don't forget to label your vectors. Okay, so this isn't entirely helpful since you haven't even seen one of these drawn yet. So let's step through a few questions, and after several of them, we will get to free body diagrams. So we're going to go through a lot of questions here. I believe there's actually 12 of them. So I encourage you to pay attention to each one, as they are very important. It'll get you some practice with these diagrams toward the end as well. So, question 1. A cart is pulled to the right, as shown below, with a constant force. It asks, how will its acceleration graph look? So this is a throwback to graphs. Take a moment to think about your answer, and then come back when you think you have it. Okay. Well, in this case, the key here is that it's being pulled with a constant force. Generally, what you want to do is think of Newton's second law here, which says F net is equal to ma. So with this in mind, it says that there's a constant force being applied. So your force, F, is not changing. Well, we know mass isn't changing. So if neither F or M are changing, well then how can A change? Right? If a net force is constant, the acceleration also has to be constant. So on an acceleration graph, that would show up as a straight horizontal line, like we see here in C. A constant force means you'll be applying a constant acceleration to the object. All right, question 2. A constant force causes an object to accelerate at 4 meters per second squared. What is the acceleration of an object with twice the mass, but the same force? I'll give you a hint. It has to do with F equals ma. Okay. The problem here is asking about the acceleration. So let me rearrange our equation. A equal F over m equal to F over m. Well, what we've done is, in this problem, it says that we are going to double the mass, right? So it says it has twice the mass. So what we're basically doing is doubling the mass. So multiply by 2 down here. But it has the same force, so 1. So we're keeping the same force. We're doubling the mass. So our acceleration is going to change by a factor of 1/2. In other words, if we started out with 4 meters per second squared, we would end up with an answer of 2 meters per second squared. And again, this holds true to our idea that if you increase the mass, you're going to decrease the acceleration. All right, let's do one more like the last. An object, when pushed with a net force F, has an acceleration of 2 meters per second squared. Now, you double the force and you quadruple the mass. Its acceleration will be what? All right. Well, again, this problem is asking about acceleration. So let me rearrange the equation again for F over m. Similar to what we did last time, let's think about by what factor we are changing things. We are saying that the force is twice as large. So you're changing the force by a factor of 2. Well, we're also quadrupling the mass, or multiplying it by 4 times. So we've changed our acceleration by a factor of 2 over 4, which is 1/2. So we have our acceleration once again. So the answer, half of 2 meters per second squared, is 1 meter per second squared. All right. Well, let's step away from the math for the rest of our questions. Let's think conceptually and then visually as well. The next 2 questions are very good. I like these ones a lot. This question says, a 40-car train travels along a straight track at 40 miles per hour. Separately, a skier speeds up as she skis downhill. Based on these 2 different situations, on which could we say that the net force is greater, if either, at all? A lot of times with this question, my students will just have a big question mark above their head. It's weird to think about, a train and a skier, and how can you compare their forces? Well, you can. You actually can tell. There's a key here. The skier is speeding up. The train is moving at 40 miles per hour. The train's moving at a constant speed. The skier is accelerating. Again, think of F equals ma. To have a force, a net force, right, we need to be accelerating. If you don't have an acceleration, you do not have a net force. So the train, even though it's this giant, massive object, has no net force acting on it. But the skier, even though we don't have a number, does have an acceleration. We know there's an acceleration because she is speeding up. So, we don't know how big the net force is, but we know it's more than 0. So the skier has the greater net force. Okay, so again, the train does not have a net force because it is not accelerating. The skier is accelerating, so they do have a net force. So the answer is B. All right, let's move on to question 5. An object on a rope is lowered at a constant speed. Which of the following is true? Okay. Well, here we should be able to recognize what forces are acting on our object. We should note that there is a weight pulling downward on the object, right? We have a weight pulling down, and there is a tension holding this object upward. So we know that there's a weight and a tension. Now, the key here is it says it's at a constant speed. As we just stated on our last question, by F equals ma, we should recognize that in order to have a net force, you would have to have an acceleration. We don't accelerate in this problem, so we do not have a net force, right? No acceleration, no net force. Which means, even though there are forces, there can't be a net force, which must mean the tension pointing up has to equal the weight pointing down, so that there is no net force. In other words, one of them isn't pulling harder in the other direction. So the answer is that they are equal. Our answer is B. Okay. Question 6. A very similar one. The only difference is, now instead of moving at a constant speed, it says that it is lowered at a decreasing speed, which is true. Okay, well, the situation is the same. We have a weight pointing downward, so I'll draw that. Here's our weight. Upward is our tension. But here is the key, and this is important. Be careful with pay attention to how I say this. It is lowered at a decreasing speed. From past lectures, we learned how to deal with the direction of acceleration. Recall that if an object is slowing down, like the object here, acceleration points in the opposite direction of the object's motion. So if our object is pointing downward, or moving downward, which it is, then our acceleration, because it's slowing down, must point in the opposite direction, or upward. So if we have an upward pointing acceleration, then we must also have an upward pointing net force. If A points up, net force points up, which means we have to have a larger force that points upward. So I'll draw that as a longer arrow for tension. So tension in this case is greater than the weight of the object, so the answer is A. So again, be careful. This is not very easy for a lot of students. We are slowing down while moving downward, which means because we're slowing down, acceleration points in the opposite direction or upward. And based on our concept of the relationship between F and A, if acceleration is pointing upward, so does the net force. So whichever force is pointing upward also has to be the larger force. That's the tension force. So the answer is A. All right. On to my favorite question out of the bunch. A mosquito runs head-on into a truck. Splat. Which of the following is true during the collision? In this case, we have to think about Newton's third law. Newton's third law states that every force occurs as an action-reaction pair, where the forces are in opposite directions, but are equal in magnitude. Equal in magnitude. Which means Perhaps surprisingly to some people, the answer is C. They will exert the same force on each other, the mosquito to the truck and the truck to the mosquito. Now this is very odd to some people, so let me just show F equals ma again. In the case of, let's say, the truck hitting the mosquito, well, think about what's going on here. The truck has a really large mass, but because the truck hits the mosquito, is it going to change its speed very much? I mean, no. The mosquito's not going to slow the truck down at all. So it has a very low acceleration. On the other hand, the mosquito has a really low mass. I mean, tiny mass. But it's just floating around having its, day, trying to ruin people's day. And then it's suddenly hit by a truck moving, 70 miles per hour. So it's going to be suddenly accelerated really quickly. So it's got a low mass and a high acceleration, but the truck has a high mass and a low acceleration. They are equal. All right. Let us now practice free body diagrams. Now that we have this background, let's try drawing them. The first of 5 of these diagram questions says an elevator, which is lifted by a cable, is moving upward and slowing down. Which is the correct diagram? All right, well, it's moving up and slowing down. We know there are 2 forces in this problem. Weight pointing downward, tension in the cable pointing upward. Like D shows, there is not a third force. It says F elevator. The force pointing upward is caused by the tension, so there isn't an extra force here. So that's irrelevant. It is moving upward, but motion is not a force. And because it is slowing down, that means there is an acceleration, which means there is a net force. We can rule out option D and E as a result now. So, keeping in mind what we said in our last question, we have a situation where we're moving up but slowing down. Slowing down means acceleration points in the opposite direction of motion, which would be downward. So if we have an acceleration that's pointing downward, we have to have a net force that is pointing downward as well. In other words, whichever force is pointing downward has to be the larger force, leaving us with the answer of C. Weight down, tension up, but because acceleration points downward, the force that's pointing downward has to be larger to give us the larger net force. All right, so that's a chain of thought processes you have to go through to get there. So be careful with these. Question 9. A ball has been tossed straight up. Which of the following is the correct free body diagram just after the ball has left the hand? As always, ignore air resistance. In this case, the ball has left the hand, meaning there are no contact forces on the ball. Nothing is physically touching it. What that means is there's only one force acting on it. It's weight. The weight due to gravity as it moves through the air. The answer is D. Any object moving through the air will only ever have one force acting on it, the weight. Assuming we're ignoring air resistance, of course. So, the answer is D. Only the weight is acting on the ball. If the ball was still in the person's hand as it was being pushed upward, then you'd certainly have an upward force. But we don't in this case. Next question. A ball is hanging from the ceiling by a string. It is pulled back and released. Which diagram below is the correct one just after the ball has been released? Like you can see on the image on the top right. All right. In this case, the first thing I'll mention is that the rope is at an angle, but it's not an object moving on a ramp or an incline. So we do not tilt our axes in this case, like shown in C, or excuse me, like shown in E. We don't tilt our axes. That is only for objects that are moving along an inclined surface. This is just a ball swinging back and forth. Let's think about one of the forces acting on this ball. One of the forces is weight. By definition, weight always points vertically downward, which means we can rule out D. D does not show the weight force pointing downward, so that is incorrect. A, B, and C all show that. So A shows that there's only the weight, but there's more than that. The object is being held up by a rope, so there should be a tension force. That tension force, by definition, always points in the direction of your rope, which is up and to the right. Both B and C show that. At this point, we just have to ask ourselves, is there a third force? C shows a third force pointing down and to the right, which is the direction of the, well, not quite. It is the direction of the object's motion. But motion is not a force. Nothing is physically pushing the ball down and to the right. There is no third force. Just to give you an idea on why it does move that way, think of vector addition, right? If you can just visualize this, say someone's pulling down on the ball here, someone's pulling up on the right to the ball there, that means the ball's going to move with a net force that points in that direction, right? Those two forces combined are going to pull the object down and to the right, which is why we see the ball doing that. Anyways, this means the answer is B. You have the weight of the ball acting downward, and the tension in the rope pointing up and to the right. Question 11. A car is parked on a hill. Which is the correct free body diagram? Well, in this case, we are on an incline, so we do tilt our axes, which all of these show. What we need to do, though, is start listing our forces. First of all, like any problem on Earth, we have a weight. We know that weight always points vertically downward. Well, D does not show a force pointing straight down. D is incorrect because of that. A, B, C, and E all show a weight force pointing straight down. Let's think of another force. This car is parked on a hill. It's parked, meaning it's not moving. So something has to be resisting its motion, and that's friction. Friction is acting to resist the motion of this car. The car wants to move down the hill, so there must be a friction force pointing up the hill. A does not show a force pointing up the hill in the x direction. B does not show a force pointing up the hill. It shows a force pointing down the hill, which is not correct. Both C and E show the weight pointing downward and a friction force pointing up the hill. So we now at this point ask ourselves, is there a third force? In this case, there is. There is a third force. The answer is C here. That third force is because the car is on a surface. A surface always pushes back perpendicularly by the normal force. So that's what we're seeing here. We're seeing a normal force pointing off the surface of the ramp, a static friction force holding the car in place, and the weight of the car pulling it downward. C is the correct free body diagram. This brings us to our very last question. There's been a lot of them. Question 12. A car is towed by a rope to the right at a constant speed. Which diagram is correct? Okay, I'm going to go through this one a little quicker since we should have some practice. We know there's a weight pulling the car downward. All of them show that. We know there is a normal force pulling or pushing upward. All of them show that. There should be a tension force in the cable pulling it forward to the right. A does not show a force to the right. But there should also be a force resisting the car's motion. It doesn't say that it's frictionless. So there should be a friction force resisting the car's motion as well, against the direction of the car, so to the left. So there isn't a force to the left in B. We can rule that one out as well. This brings us to options C, D, and E. All of these show the correct 4 forces, but there's a difference. C shows that the tension is greater than the friction. Oops, that's normal force. This is weight. Imagine using the same letters over here. In D, the 2 forces, friction and tension, are the same. And in E, the friction is the larger of the 2. Well, keep in mind, it says that this is moving at a constant speed. That means there is no net force. So all of the forces should be equal and opposite, and that's what D shows. D shows our equal and opposite forces. So that is our answer. All right, so at this point, we've at least introduced what a free body diagram is now and how to draw them. So in the future, we will actually be drawing them ourselves from scratch, not just picking them from a multiple choice question. So hopefully, at least for now, this has given you at least a basic understanding of what they look like and how they will be drawn. In our next lecture, we will start to add some math into all of this and start drawing these ourselves. But until then, thanks for watching and have a great day.